Okay, I don't know if we're on or not, but I'll assume that we are. Good afternoon, if it is afternoon where you are, sports fans. My name is Seth Shostak. This is SETI Live, coming to you today with a really interesting topic, which is which star systems are likely to have resident astronomers on a planet somewhere around them that would know about Earth. We're going to talk about that with two professors of astronomy. And, it's a very interesting result because it may give us a good clue as to where we should look for some cosmic company. But first, I've got to remind you about something, and that is that today's not just another Tuesday. Yeah, you remember it was Thanksgiving last week, and then there was Black Friday, and then there was Digital Monday, and then there was something else, Sunday. I mean, all these special days. Well, today is Giving Tuesday. Giving Tuesday. And I want to point out to you, and I think many of you already know this, the SETI Institute is a nonprofit organization. And as a consequence, we have to raise money in order to do the kind of work that's done here. But there's actually a special opportunity today. If you go to the SETI Institute website and you make a donation, it can be anywhere from, $10 to $1 million, whatever you got. But if you make that donation, one of our board members, well, he's not a board member actually, but he's one of our donors, will give $10,000 to the Institute if 200 of you do that. Now, I got to say, we've been busy all morning, trolling people on the street. So we already have 100 people. So we only need 100 more to make this. So please, what you give is not as important as that you give, right? Okay, we'll get right back to that. Let me introduce today's guests. You can see them on the screen there. Against that blue background of some weird planet is Lisa Kaltenegger. Lisa is a professor of astronomy at Cornell University, and I believe that's in upstate New York. At least it was before they moved it. Also here is Josh Pepper. Josh is also a professor of astronomy, also physics at Lehigh University, which is somewhat to the south. That's in Pennsylvania, eastern Pennsylvania. And the two of these have written a paper. I think Lisa was first author and Joshua was second author. I don't know how many more there were today. Today's research papers usually have at least a minimum of 500 authors.
Only two. Only two.
Only two. All right. That's
it was
great.
Two partners in crime. We did this without any other interference. It was Josh and me all the way.
Okay. Well, there you go. Anyhow, so the idea here was to pick out stars, nearby stars, where it's reasonable to suspect that if they have intelligent life on a planet around these stars, and they can fund some astronomy research, those planets, those societies might know about us. So let's begin by saying, well, I mean, what's the deal here? How can you do that? So, Lisa, why don't you delve in there and tell us what the idea was?
Let me just give you a little bit of a different take on this. But the idea really is, what do we do? You, me? How are we trying to find life out there in the universe? And it's amazing that we live in the time where we have the tools to do that. Whether there's life out there, we don't know, but we actually just got closer and closer with the big telescopes that we're building right now, the James Webb's going to fly next year, where we can hopefully, for the first time, see what's in the air of these other planets, in addition to figuring out if there's technology signatures. But we were like, okay, so what do? We are trying to find planets that block part of the stellar light. If this is the sun, and this is the planet, they block part of the stellar light from our view temporarily. It's called a transit. A star is a hot ball of gas, so it's bright. And if a planet goes between our line of sight and the star, it's temporarily just a little bit less bright. And while it's in front of the star, part of the light from the star gets filtered through the atmosphere of the planet. And so you could figure out whether or not there's signs like oxygen that we breathe, right? And then we said, okay, so we're looking for that. But now let's flip the perspective. If somebody else who might be out there or not would be doing the exact same thing, which stars could see us that way, could see our beautiful pale blue dot, the Earth, block out just a little bit of the light from the sun? And so Josh is an expert on stars, and I'm trying to find life in the universe in the air of this other planet. So we figured we'll team up, and we're both in NASA's test mission that's currently looking at all the sky, trying to figure out where there are such planets out there, to flip our vantage point and figure out which are the closest stars that could do that. And I don't know, Josh, do you want to take it away and say how 2 or 3 stars we could pick out, or how we got into the thousands?
Yeah, let me just point out before you go into that, Josh. All right, so the idea is you want to know which stars could see the Earth blocking part of the sun. Obviously, a star up above the plane of the ecliptic here is never going to see that because the Earth never gets in front of the sun. Maybe 2% of all stars might see that. Josh, how did you figure this out?
Yeah, so I mean, you're absolutely right. It's really only looking for the stars that are in or near the ecliptic, following the stars that are in the path of the sky that would see the Earth moving and transiting in front of the sun from their perspective. So the way that we tried to approach this was really asking the question, well, how well do we know the positions and properties of the stars in the sky? And the way that we approached this was there was a fantastic mission launched by the European Space Agency a few years ago called Gaia, which has absolutely transformed our understanding of all of the stars in the neighborhood around the sun, our understanding of the Milky Way, and dozens of other topics in astrophysics. But one of the things it tells us is a lot more about the properties of nearby stars and their exact positions and movements in the sky. And what we did is we used part of the Gaia mission observations to combine that with other existing catalogs of stars and stellar properties. And we were able to create this catalog of billions of stars that we used to plan the TESS mission. Now, what Lisa and I did, we took the particular stars that were in that catalog and said, okay, here's the spots on the sky where if there is a star there, then that star could have a planet that would see us transit, which is fantastic. But the other thing that we also did was we asked which of those stars are ones that could conceivably have a habitable planet or a civilization. So remember, when we look out into the sky, a lot of those stars are not nice, quiet dwarf stars like our sun, but are giant stars that are evolved and they couldn't have any habitable zone planets or other kinds of problems. And so that's what we were able to do, was pick out the 1,000 or so stars that are just perfectly well positioned, both in location and at the right stage of their evolution, where they could have a habitable zone planet that could look back and see us transit.
Okay, look.
And so as Josh has beautifully put it, it's location and time that you want to optimize, because just at the right time where the sun doesn't just blow up and gobble up its planet, right? And just at the right location to actually see us and get curious about whether or not there's life on our planet too.
Well, if you're worried about them blowing up, that must mean that you that you have some concern for their welfare. But I mean, beyond that, I mean, you could only go out so far with this project, right? As stars that are beyond a certain distance aren't going to be in your list, even if they, in principle, could see a dimming of the sun every 365 days. How far away were the farthest stars then, Josh?
We just went out to 100 parsecs, which is roughly 300 light years, which is a pretty good volume containing, that distance will just contain in that volume hundreds of thousands of stars, millions actually. But we just went out that far because the further away a star is, the less information we're able to gather about it, the less we're able to investigate it. And so by limiting ourselves just to the closest stars that will be in that right position, that enables us to concentrate on the best places to look for possibly habitable planets.
Okay, but let me ask this then. I mean, let's say that 1 in a million stars, I mean, just to take a number, 1 in a million stars has a planet where there are some sophisticated aliens, right? The aliens who like, I don't know, piano concertos or something. They're sophisticated. Is any of the ones you studied likely to make the grade? I mean, 1 in a million?
Well, the good thing is that we are better in terms of just trying to figure out if there are planets around these stars than 1 in a million, because we know that 1 out of 5 stars has a planet that's just at the right distance, not too hot, not too cold, and then small enough that it should be a rock like the Earth. So that's great ingredients. We have no clue how easy or hard it is to make life, so we don't know if there's life. And then, as you said, we also don't know yet if that automatically means that the civilizations, if they're there, will get to the point where they're going to use technology, and also whether or not they're curious in the first place. So maybe that's where your 1 in a million comes from. But the great thing is it's like 1 out of 5 has a planet that's potentially like the Earth. And so if you have 1,000, we have 1,004 stars within this 300 light years. I like the numbers. I like our chances. And yes, some of the stars are very young, right? So maybe not much has happened yet. Maybe you have like the first microbes crawling around, trying to like pollute the air with nice chemicals that I can see in the telescopes when they come online, like with the James Webb next year. But it's great that we just say these are the closest ones, because we get enough light so that with the telescopes we have, we can do something and we can analyze it. And as you said, 1 in a million, if you're talking advanced, then they better have bigger telescopes and can see further out, because they have the light collecting capability. We are just doing the first steps in that kind of exploration.
So we're kind of assuming that they're at least, I don't know, 100 years more advanced than we are. But in the lifetime of the cosmos, 100 years is not much. I'm just going to very briefly interrupt this to tell everybody who's watching, not by first name, because that would be embarrassing for them. But we have people in Scotland, Australia, India, Ireland, Pakistan, Netherlands, Deutschland, Belgium, Portugal, Wisconsin. Wisconsin recently withdrew from the U.S., apparently. Glasgow, Liverpool. That's terrific. And also, remember, it's Giving Tuesday. We're trying to get to 200 people. This sounds like a begathon, right? NPR begathon? Well, sort of. But we just had 2 donations from people who are watching this. Voyager Girl donated $100, and Randy Lee donated $15 on Facebook. So, only 98 more of you donate, then we get this extra $10,000, and the Institute may buy me a coffee mug or not. All right, let's try turning this whole idea around, because it's a very clever idea that, we can tell which of among the many, many stars within 300 light years, Josh has already said it's millions, might know about us, might know something about the Earth, because they could find oxygen in our atmosphere. But if we follow this,
can I just like have one point? Right now it makes it sound as we are the first ones who've ever thought about this. It's like we just made the best catalog possible right now with this amazing Gaia mission. But this idea, luckily, because humankind is a really curious and interesting species and has good ideas once in a while, has been around for a while. And there were some SETI papers that exactly asked that questions tens and tens of years ago, decades ago. We just were in the amazing position to be able, with this new Gaia satellite, to finally get us a real list with great parameters. So what astronomers and everybody else can use to pick out exactly the one that Josh was saying, that are not too big, not too old, not too, I don't know, whatever you want to say, but just the best list that you guys and us with the telescopes to look for kind of air molecules that indicate life, you for looking for, I don't know, radio signals or lasers. Now we have a great list in our solar neighborhood, but this is not Josh's and my early, first idea. This is, as always in science, and that's what I love about science, standing on the shoulders of giants. Everybody does a little bit more until we get to where we all can use that.
Yeah, that sounds like what Newton said, but he was making a sarcastic remark about Hooke. All right, never mind that. But I'm glad you said this, because actually I think the first, or maybe there was the second paper on this subject, was actually written by a guy at the Space Telescope Science Institute and myself, believe it or not.
Mm-hmm.
So
yeah, we cited you, I promise.
Oh, great. Maybe I'll get a job. All right, now, okay, but we should explain what that idea was, because it's to take the kind of work you're doing and turn it around. Because if the aliens are looking at the sun, there's some grad student who's tasked with doing that because it's really boring. But then they see that every 365 days, the sun gets 0.01% dimmer or whatever. They might send a signal, if they're trying to be garrulous or at least just be friendly, they might send a signal that arrives here at Earth just at the moment when we're transiting the sun, because that event is kind of like a clock. And so this would tell SETI scientists where to look and when, and maybe that would increase the chances that our next conversation will be whether the the aliens on this planet breathe oxygen or methane or chlorofluorocarbons, right? Yeah.
Well,
I think, that's the hope. Sorry, Josh, go.
Well, no, I mean, I think that's a really great idea, because one of the challenges in trying to think about communicating with another civilization, if you don't already have an existing communication channel, is to ask the question, well, when do you look? When is it viable to do that? And on the one hand, you could spend all time just putting out energy and signals in all directions at all times, but it takes a huge amount of time and energy and effort. But if you know exactly where and when to look, the clock that a transit makes in front of its of a planet makes in front of its star is a great way to note the right time to look at that particular place.
Okay, so this is a way to second guess the aliens, and by doing so, increase the chances that you'll make contact of some sort.
And so, Seth, sorry.
Go ahead, Lisa.
I was just saying, Seth, you were saying before is like why we didn't go further out, right? So Josh was saying we did 100 parsecs, which translates into roughly 325 light years. So, if you go back 325 or 300 years in humankind's evolution, I don't know how extremely exciting we were already. So we were basically saying if we had a time limit too for people getting our signals, we're just starting 300 years ago, maybe 100 years ago, but let's say 300 years ago, let's give us the benefit of a doubt. We'll be starting to become interesting in case they're not just looking for life, but maybe even for somebody who have a conversation with if there's life out there, because we haven't figured out whether or not we're not alone. But the numbers seem to be forever in our favor.
Yeah, well, I mean, that's really a good point. It's a little subtle, but it's an excellent point that, to encourage them to broadcast in our direction, they would presumably want to know that there's somebody here smarter than, a cabbage or something else that makes oxygen that pollutes the atmosphere, right? And they would only know that if they were within, 50 light years or something like that, where they might have picked up some of our television, our radar, stuff like that. So and how many of these star systems are within, let's say, 50 light years? Josh, do you have that number on the
I really should have looked it up before this call. Lisa, did you do that?
I think we had somewhere around like 100, 200. We were looking at the 10 parsec ones. 10 and 20 parsecs, so something like that. But it was somewhere around the 100. But this is one of the things we can always look up later. This will be forever a mystery.
Okay, but I don't know if that's going to help people here. By the way, we have more people tuning in. Yeah,
there is, I know that this is but in case somebody has, or looks at the paper, so you basically see that we have it shown by distance, and so I take my word from before back. So if you're talking just about 50 light years, there's not so many. But if you talk about, I was thinking about 50 parsecs, what's a bad thing for astronomers, because light years and parsecs are not the same. There's a factor of 3 between the two. But so if you go within about 100, 150 light years, then you get about 200 objects. But if you only go about 50 light years, then there's meager picking, but among the meager pickings, there are actually some interesting stars. And so even then.
Yeah, it's like maybe winning the lottery. Yes, the difference between parsecs and, I mean, even astronomers will admit that parsecs, which goes back to the history of astronomy, why it was chosen at all, it's not even a very great unit of measurement. It just confuses everybody, including Harrison Ford, right? When he said how many parsecs it took him to go to lunch or something like that. We have people in Kentucky, Warsaw. We have a bunch of questions here too. Florida, Norway, and they are comparable. Montreal, Chicago, Austria, the Ukraine. I had relatives that came there. All right, let's. Shall we go to questions or?
Let me just put one more thing on, and then we go to questions. Just because I know that I'm sure you have a great audience who knows all of this, but just in case this was a little bit fast for everyone, light needs time to travel like a car. If you go from New York to Ithaca and you drive a certain speed, it'll take you 4 hours. That's it, right? And astronomers need to measure the universe that's so much bigger with something faster than a car. So we use light, the fastest speed. And so if we say something is 100 light years away, what that means is that light will take 100 years to get to us. And I'm sure you all got that, but just to clarify it, because we keep throwing light years around and we say that parsecs is tricky. But if you haven't thought about that it takes light to travel distances, then light years makes no sense. So light years is a distance, and it's a beautiful name thing. Like we call it light year, but it's really something like miles or kilometers. So just to put that in, and then I think the question is going to be easier.
I hope the viewers can figure out that both of our guests today teach. Okay, so there you go. I mean, maybe we'll go into a few questions here and see how we're doing here. By the way, the number of people that have contributed to the SETI Institute's fundraising drive here on Giving Tuesday is up to 111. So only 89 more to go. Now, those of you with multiple personalities can only count as one, but please try donating. The amount is not so important as the number. The number, if it's 200, then we get $10,000 from a rather generous guy here in the Silicon Valley. All right, let me see if I can read some of these questions here because they are. Here's one from Dan. An entity more advanced than us, like after hitting the singularity. Oh, I see what you're saying. Okay, so technically more advanced being wouldn't have our scientific and technical limitations and would have no problem to find and observe us, right? I mean, you know, this idea of using this transit method where the Earth gets in front of the sun. Maybe they could just have a super duper telescope and just find the Earth directly no matter where in the sky they are.
Yeah, so that is definitely true. However, if they were trying to contact us, for example, they would know that we still have quite some limitations and that we might only be looking exactly at the time when we block the view of our sun for them, because as Josh said before, it's a lot of energy and time to just basically broadcast or look at all the time, all the different stars in all the different times. And so this is also for SETI, right? You have like targets, more important one than others. So I think however far advanced, if you think there's life there and it might way advanced beyond us, yes, they could find us. But could we actually figure out that they were trying to find us or trying to make contact? That would be a special moment in time where we might be more likely to look.
That's an excellent point, that in fact, they might know about us, but we don't know when to look for them. Whereas if they're using this transit method, that tells us when to look for them, right? But you know, do you happen to know how big a telescope it would take to find Earth directly? Suppose they were, 100 light years away and they're looking at Earth. They'd need something bigger than TESS. They'd need something pretty big to see the Earth directly, would they not?
Well, these are things that already we're working on here on Earth. So NASA and the European Space Agency are working on future telescopes that would have the ability to directly see a planet like the Earth at the Earth-like distance from its star. They are being planned for launch, hopefully in about 20 years or so, depending on how things go. But there are telescopes that we have the technology to at least start developing now that would have that ability. Maybe not to 100 parsecs, but I think to something like 10 to 20 parsecs, 30 to 40 light years or so. But that is a technology that we are in the midst of developing now. We don't quite have it yet, but it is on the horizon. Oh, well, so it's not that much further advanced.
No, and you consider, the first telescope for astronomy, all right, it was like 1600, right? 1609, I guess Galileo found the moons of Jupiter or something. And in 400 years, we've gone from that toy to things that sit on, the tops of mountains in Hawaii. What would a society 1,000 or 1,000,000 years more advanced than ours have? Presumably, they'd be able to do all that.
But the key thing in this, again, right, is that why we are doing the transits right now is because they actually allow us to see the planets easier. Because if you try to find a planet like a pale blue dot, remember this beautiful image that Carl Sagan did, where we see our own planet as this tiny dot of light? Usually there's a huge star next to this tiny dot of light. And so you have to block out that star's light. And that's the hard thing to do, to get enough light from this tiny dim point, the planet, that only reflects part of the starlight or is warm and thus emits a little bit of heat, but nothing compared to its big host star. And just for comparison in terms of size, if you put the Earth 110 times next to each other, like pearls on a string, that's the diameter of the sun. So trying to find this tiny, tiny planet around a huge star, bright one, is hard. And this is why we're first going with the transits. But yeah, in the long run, exactly as Josh said, we are working on technologies to do that, but it is super hard to actually block such a huge bright objects. There's a billion photons from the star for one tiny meager one from an Earth-like planet next to it. So we're working on being good enough to get rid of all that light from the star to find the planet, but it's hard. But it's a great technical challenge that we're advancing on.
Well, maybe one of the people watching this SETI Live will do it. I once heard it said, and I think it kind of checks out, that finding the planets next to a star like the sun is equivalent to finding a firefly orbiting a Hollywood searchlight from 10,000 miles away. I tried that once. It didn't work. Okay, let me just go to a couple more questions here so that we get them in here. Let's see. All right. These are really excellent questions. I mean, I don't know. We must have a higher grade audience today. How long does this is from J Jam? How long does it take Earth to transit the sun from their point of view? Excellent question.
Up to 12.6 hours if it goes in the middle of the sun, right? Because if you just don't see it perfectly straight, then it gets less and less and less. But if you just see it perfectly straight, it takes it takes 12.6 hours to go from one side to the other.
Oh.
And we did a second limit in our paper catalog and said, okay, and these stars would see the Earth for at least 10 hours transit the sun to get enough light to figure out what's in the atmosphere of the planet while that happens.
Here's a question from actually an interesting answer. Anybody in the audience who's old enough to remember the transits of Venus, right? That happened like 15 years ago. I don't know exactly. Right. You may notice that Venus didn't necessarily go across the equator, if you will, of the sun. It went above it or below it. And so it took a little less time here. This is from Padilla Art. Aren't we getting radio signals from some galaxy nearby? Well, we're not getting...
I think, Seth, that's your answer.
Well, of course we are. We used to study those emissions, but they're all natural emissions. Mostly, there's always some activity in the center of a galaxy that often makes radio emissions, big black holes, stuff like that. But also, all the hydrogen gas in the galaxy is producing radio noise too. But we've not picked up any signals that were made by a transmitter. They're made by nature. So that's the answer to that. Here's from Cliff. How many civilizations may exist at the technical level? The trouble is I never learned to read. How many civilizations may exist at the technological level of, say, Rome are close to us? Well, if you have the answer to that, I'm impressed. Anybody have the answer to that?
Well, one of the important things to remember is that the difference between Rome and us, let's say just take it as around 2,000 years, is incredibly small in the development of humanity, let alone multicellular life or life in general. So, thinking about the differences between the most primitive human civilization, the most advanced human civilization, is still in the blink of an eye compared to the development of animal life, for instance, or life in general. So when we start thinking about kind of the ages of other civilizations, there's sort of like a instability that goes on, because the difference between seeing something at the most primitive caveman level of life to what we might envision 1,000 years from now is still a blink of an eye. So that's one of the challenges, as you guys all know with SETI, is how to think carefully about the technological level of an alien civilization.
Yeah, that's also why we won't find any societies that are, not in advance of us. There will be more advanced, because you're not going to find them if they're less advanced. They're like the Romans. I mean, the Romans were pretty good at things like literature and law, but they weren't great at radio technology. So, you're not going to find those guys. And the chances that they're going to be in even 100 or 1,000 years of what Homo sapiens has done today is pretty small, just for the reasons you mentioned. Lisa.
But the great thing about it, just to build up on Josh's point, so if you take life on the Earth and think about it as a 24-hour clock, then life started roughly at 3 a.m. And at around lunchtime, it actually started to make oxygen in the atmosphere. So before that, it made methane and CO2, and it was really hard to tell that apart from geological activity. But as soon as it actually makes oxygen with a reducing gas like methane, and that's now complicated, but believe me for now, then we have no other explanation that on that planet there's life. And in this 24-hour clock, us humans, we come onto this 24-hour clock of life, that's 4.6 billion years of the evolution of Earth, about a second before midnight. So if you want to find you and me, you have a much harder goal than if you want to find life. And so by actually looking at the atmosphere of these planets, what we're hoping to do is give you a potpourri or a diverse set of planets with signs of life. And which ones of those then would have advanced life? And then you have to decide what intelligent life means, if we're intelligent or not. Is it tardigrade intelligence? All of this thing is super interesting, but just decide. There is life, and there has been life on the Earth since about 3.5 billion years. And since about 2 billion years, we can actually tell, or if somebody looked at our planet, they would see telltale signs of life on our planet for about 2 billion years. Then if you're asking me how many, we don't even know if there's life out there, right? And so if you're asking me how many of those are Roman empires versus, as Josh was saying, blink of an eye more, us, or blink of an eye more, I don't know what's going to happen later. We don't know. But that also makes the whole search so exciting, right? If we knew what we were to find, it would be a little bit boring because we have no idea. It's even more exciting to look.
Yeah, if they have Corinthian columns, and they probably won't. Actually, your answer, Lisa, plays right into a question from Simon, who says, what kind of environmental impact is visible from far away? Deforestation, composition of the atmosphere, maybe those chlorofluorocarbons. What would be visible to aliens who had no limitation on their budgets?
So the interesting thing is that what we are looking for now in these really, really hard to do telescopes where we block out the light from the star, what we are looking for is big things in the atmosphere, big concentrations. We're looking for oxygen, for methane, for water, and then for CO2 to figure out how hot it is. But if you want to tease out technological gases, technological signatures in the air, like CFCs, sorry, like that come out from your fridge, right? Those need a lot bigger telescopes. And then the question is, how big that telescope? Well, that depends how much of it is in the atmosphere, right? And so there was a running joke when they were saying, if we can actually find those CFCs in the atmosphere, then we know there was a civilization not as smart as us that didn't figure out that they destroy the ozone hole. And so finding a lot of it might not be a good thing about finding intelligent life, but definitely finding life that has generated technological gases, right? And so there's a lot of research going on, but luckily, right, those gases currently and hopefully in the future are only a very, very tiny part of the makeup of our atmosphere. And we'd better keep it that way because you and me would love to breathe, I assume.
Yeah, but I'd like to be well coiffed. Not that I am. Okay, so there is that. All right, let's take another question or two here from Bernd. What about your search without the Arecibo Observatory? I think people are aware that the Arecibo Observatory had an accident a couple of weeks ago, and actually a couple of months ago, pieces falling off. And today, a large majority of the feeds, or all of the feed structure where the receivers are, collapsed into the dish. It's pretty messy looking. You can go online and see that. How does this affect your research? Josh?
Oh, I mean, I'm an optical astronomer. I'm not a radio astronomer. I'd be much more concerned about how it affects your work with radio searches for civilizations, as well as all the many radio astronomers who use that for things like pulsars and studying galaxies. Lisa, are you familiar with like any of the radio people and how they're being affected?
I basically think exactly like you. We push this back to Seth because he has way more of an insight how this influences people. Because yes, it influences a huge part of the astronomy community, and it's not just searching for extraterrestrial intelligence. You can do so much with these radio telescopes. What allowed us, or what allowed the SETI Institute, for example, to do part of that search, because they were getting grants for science that was not that search, and could do SETI as a piggyback, I would say. But in a way, I should give this back to Seth before I say something completely wrong.
No,
but
no, no. I'm not the guest here. Just very quickly, then, I will say that the SETI searches these days obviously have made use of Arecibo. Those are obviously not going to happen until either you move your experiment to another telescope, and that happens, or they repair it, which is maybe not so likely. But in any case, it would be a perfect instrument to follow up with the star systems that Lisa and Josh have categorized, because it can see the ecliptic, right? It can point to stars in the ecliptic, so it would be perfect. So in that sense, it's a loss. It's a big loss, no matter how you look at it. And Lisa's right. It's mostly used actually for studying pulsars and quasars and small galaxies, believe it or not. Let's see if there's another question here from Maxentius. Is an oxygen atmosphere a guaranteed biosignature? Lisa, you've talked a lot about that. Is it guaranteed, or maybe a planet just has a lot of oxygen and there's no life there?
The key thing is oxygen alone is not enough, right? It's sometimes easy to say that's what we breathe, but if you split water, you get oxygen. If you split CO2, you get oxygen. So the trick is that you have to see the oxygen in combination with the gas that it reacts with. And so methane, for example, is a reducing gas. So oxygen and methane mix CO2 and water. So if you find a planet and in the atmosphere, you find a signature of oxygen or ozone, doesn't really matter which of the two, and a reducing gas like methane at the same time, that now tells you that something right now is producing this oxygen, because it will react with CH4 to something else. And that's our indicator that there's life on that planet. And what I hopefully said before is just kind of what we're going to go for is we have no other explanation but life, right? And then there would be a lot of people who's like, oh yeah, but well, I don't know, this and this and this. And that's exactly how science works, right? We come up with other ideas because extraordinary discoveries require extraordinary evidence, as Carl Sagan said, right? And so the fun part for me is that the search for life in the atmosphere on the surface of the planet goes hand in hand with the search for intelligent life like SETI is doing it. Because I promise you, if somebody sends us a high signal, right, you will not necessarily question it as long as it's in a language you can understand, right? And say, oh yeah, we found life. If I find oxygen with methane, there would be a lot of questions, as there should be. But the search for life in general, if you think about the 24-hour clock, the 4.6 billion years in life on this planet, affords you to find life in all its different stages or in more. In the beginning, when it only produced CH4 or CO2, we can't tell it apart from just a volcano, basically. But as soon as oxygen comes on and there's this reducing gas, now we have 2 billion years in Earth's history where somebody could have said, there's life on this planet. What kind of life? Dinosaurs, flamingos, single cells, somebody who's thinking about life in the universe? That is a completely different question. And for that, we would need huge telescopes to figure out if they're like technological gases, or we would look with radio signals. But what we were really going to do is we're going to make a mesh of this. If we find an interesting signal, we're going to basically point all of our different instruments to it and try to find as much as we can. And hopefully there's going to be a radio signal or a laser or, whatever it is. We'll just all going to pull our resources together and figure out what we see.
All right. Well, we're running out of time. We're going to take one more question. I think that's worth pointing out. I mean, anybody in the galaxy, there's been all this oxygen for what, roughly 2 billion years, right? So anybody who's in the galaxy, which is only, 100,000 light years across, if they have a big enough telescope, then they would know that Earth has life. And if life is very common, we don't know that, but if it is a very common thing, then maybe in the back of all their Astronomy 101 textbooks, there's a long list of all solar systems known to have some sort of biology. They wouldn't know that we like opera or any of that sort of stuff if we do, but they would know at least that there's some sort of oxygen burning metabolism or producing metabolism here. All right, I'm going to tell you where we are on the donations front. And for those of you who tuned in late, let me just remind you, this is Giving Tuesday, so you really ought to give something. And the SETI Institute, you'll feel better. You'll sleep better at night, right? And if you sleep better at night, then that dog on your bed will sleep better at night. So here's the thing. We run as, a nonprofit. The SETI Institute runs as a nonprofit. And so much of our research, and in particular, all the SETI research depends on donations. So we have this pledge from another donor that if we get 200 donors to give something today, no specified amount. If they give something today, 200 of them, he'll give $10,000. So that's a significant amount of money. So please go to the SETI Institute website, which, by the way, I probably didn't even tell you where the website is, but it's SETI.org, as in organism, but it's actually organization. All right, let's take one more question and let these people get back to mapping the cosmos. This is from Dean. How big could you go with the terrestrial telescopes, and can we build that to zoom in on a planet? In other words, could we build a huge telescope, either here on Earth or in space or on the moon or something, and be actually able to see features directly on somebody else's planet?
Well, people have thought about this, and people have thought about schematic designs for how that would work. Really, the way we would probably do it is you'd probably want to launch telescopes into space, but rather than one single big monolithic telescope, that would just be one big circle, you'd probably have a whole swarm of floating telescopes that would all be connected via laser beams. So what they would do is they would all gather the light into those individual telescopes and then combine the light together using a process called interferometry. This is a way of combining light, of resolving a signal that you wouldn't otherwise be able to do between multiple different vantage points. And that's a very exciting way of potentially doing it. And that's the kind of thing maybe we can do if we do discover, say, a planet with a detectable surface that has an atmosphere that we're already seeing intriguing signs of life. Then that might be enough of an impetus for us as a civilization to build an observatory like that, maybe in 40 or 50 years from now, if we're really, gunning for that kind of level of commitment to the science.
Okay, but it still wouldn't be able to see, for example, the state of New Jersey at 100 light years.
You could build a swarm of 10-meter class telescopes in space, each of which would cost, levels beyond what NASA has money for. But you could build a swarm of 10-meter telescopes that could resolve a picture of the Earth to get something like about 10 by 10 pixels in size. That is physically doable with a swarm of telescopes of the size that we can build. The challenge really is the engineering and data processing for how to merge all those signals. And frankly, it's the cost. That's far and above beyond what any existing scientific project is able to do right now.
Lisa,
the interesting thing, sorry, go.
I was just going to ask you, what is the biggest telescope being built now?
So let me answer this in a second, but basically what Josh was saying is completely right. One of the things that we sometimes forget is actually, if you see an Earth and if it rotates, right, there's actually something like cloud features that are randomly everywhere if you just look long enough. And so what you're starting to see after a while, take clouds out of the picture, you start to see some kind of patterns. And so from those patterns, even before these big telescopes, you should be able to infer, oh, there's something darkish, there's something brighter. So there's oceans are very dark, they don't reflect much. There's continents. It's gonna still take a lot of time, right? But a lot of times we think about, we need a picture of something. There's a lot astronomers can do and have always done with the little bit of light we get, whether we split it into its colors to figure out which different kinds of molecules are in the atmosphere, because there's less light coming through if light actually hit the molecule, made it rotate and vibrate instead of just going straight through to my telescope. Or if we are intelligent about how we actually see the patterns, and human brains are great trying to see patterns, right? To figure out a little bit more, even without a picture, about things like bright spots and less bright spots on a planet, like continents or not. And the biggest telescope being built right now is currently the extremely large telescope in Chile in the Atacama Desert, dry and high up, so not too much noise in the atmosphere when we look. So the stars twinkle just a little bit less when it's dry and high up in the atmosphere than when you're on the ground. And so basically that's where we're building a bit more than 38 meters, so let's say 40-meter telescope in the Atacama Desert, exactly in a way like Josh described it, not interferometric, but with different mirrors that we put together into one big mirror, because that's what we already do for these big telescopes. And if we do it in space, and if it could free fly, what that would give you, you could actually just expand your telescope out in this interferometry, right? So if they were all close together, you'd have this much of the space. But if you can let them fly further and further away from each other, drift away in time, you could basically mimic having telescopes of many, many different sizes. And by chopping them up in smaller pieces, like 10 meters is maybe not a small piece, but smaller pieces, then you can actually get them in a rocket, because that's the next problem. How do you get it to space? It has to fit in the rocket, because JWST is 6 meters in space. It's going to launch Halloween next year, and it's amazing. I'm looking forward to it. But one of the scariest things I've ever seen is the unfolding mechanism for JWST, how it unfolds and how it refolds itself in space. But I like origami, and I like paper folding and pop-up books, so I believe we can do this.
Telescope origami. Well, I'm going to bring this to a close. That's kind of interesting, though. The extremely large telescope or outrageously large telescope, right? At 38 meters, that makes it about 120 feet, something like that. And I may be wrong, but I think that the Hubble Space Telescope mirror was like 120 inches. Maybe that's wrong. Is that wrong, or is that right?
I think that's about right. It was
Yeah.
what,
It's certainly within a factor of 2 or 3, which for astronomy is pretty good. So if it's 120 inches, this is going to be 120 feet. I mean, that in only 25 years or thereabouts. All right, we've gotten a couple of more donations. We're at 121 donations. Stella Billy just donated $13. An interesting number. That I hope that wasn't your allowance, Stella. Anyhow, I want to thank our guests today, Lisa Kaltenegger, Joshua Pepper, for being with us and talking about, who's likely to know about Earth. And I recommend that all of you go visit the SETI Institute website, even if you don't donate. Just go there, check it out, SETI.org, and we'll see you next week on SETI Live. Thanks very much.
Thank you.